In this video, I will introduce the concept of implicit differentiation. But first we have to talk about what implicit versus explicit even means. So let's do a quick comparison. What you are used to is explicit. An explicit function might look something like this: y equals x squared. Notice that we have y all by itself on one side of the equation. And then we can graph it very easily. And this one in particular we know to be a parabola like this. And now we have learned to differentiate equations like this. So we could say y prime will equal 2x because of the power rule. Now, what if I wanted to know the slope at x equals 3? The slope right here. Well, we could just substitute 3 into the derivative, and that's going to give us the slope. So the slope at 3 would be 2 times 3, which would be 6. So the slope right here at this point is 6. That's how it works for explicit. That's pretty much what we've been doing this entire time. Now, there are other types of equations that you are very familiar with that don't quite work like this. And these are called implicit equations, implicit functions. So here's an implicit formula: x squared plus y squared is equal to 16. When I tell you y equals x squared, you automatically know that's a parabola. You should be able to recognize this as a common shape, something that you should know. Hopefully, you're jumping out at the screen and saying, that's a circle. Okay, this is the equation of a circle with a radius of 4. Okay, so what if I wanted to find the slope at this point right here, for example? What if I want to find the slope right here? All right, that was really easy to do when we had an explicitly defined formula. Y equals x squared. We could just do the power rule or whatever it may be, and we found the slope very easily. But how do we differentiate when y is not by itself? So of course we could try to convert this equation to an explicit form. We could try to solve this for y. And so if we try to do that, we could subtract x squared from both sides. So we'd have y squared is equal to 16 minus x squared. But then we'd have to take the square root of both sides, and that would give us y is equal to the plus or minus the square root of 16 minus x squared. And we could go on to use the chain rule, but we'd have to figure out what to do with the plus or minus and all of this. There's an easier way, there's a better way to differentiate an equation like this, an implicit equation, rather than trying to make it explicit, which sometimes is really difficult, sometimes even impossible to do. So time to learn about implicit differentiation. So in case you're taking notes, here are the 4 steps of implicit differentiation. Step 1, we will differentiate both sides of the equation with respect to x. So let's go ahead and apply these 4 steps in context as we do example 1. So I'm just going to recopy this problem to sort of spread things out a little bit. So we've got x squared plus y squared is equal to 16. So we are supposed to differentiate both sides of the equation with respect to x. So I'm going to do dy dx in front of each of these things. So as I take the derivative of the left side, all right, dy dx, we know that we can differentiate across addition. We can just do each part separately. So I'm just going to skip straight to the part where I do each of these separately. So I'm going to do my dy, well, not dy, I'm going to do d dx to show that I'm taking the derivative of this term. And then I'm going to do d dx here. And then, of course, on the right-hand side, I'm going to do my d dx as well. So that's the first step. So let's go ahead and follow through on that. The derivative of x squared is just going to be 2x. All right, now this next step is something new. Notice that we are differentiating with respect to x. And then the variable that we see right here is x. So we can just do the power rule and get the answer like we always do. But when we get to the next term, we see something different. We're differentiating with respect to x, yet the variable is a y. The variable is different. Whenever this happens, you're going to have to actually do the chain rule. So first we're going to do the derivative of the outer function. So we're going to take the derivative by doing the power rule, and that's going to give us 2y. But then we have to take the derivative of what really is the inner function, which is y itself. But because this is not an x, we have to do this extra step and put dy dx. All right, we are taking the derivative of the y separately because this y is understood to be a function of x, and so we have to do the chain rule. So look, it's a little bit murky when you just try to think about it, but it boils down to this. If the variables are different, like you have an x and then a y, go ahead and do the rule, like the power rule or whatever you're doing. Go ahead and take the derivative of the outer function, but then you're going to need this extra dy dx, or really whatever this variable is. If this had been a p or an n or anything other than x, you would do like dp dx, or whatever it was. Okay, now moving on. The derivative of a constant is 0. We know this. So we have now completed step 1. So step 2 is to collect all terms involving dy dx on the left side and move all other terms to the right side of the equation. Okay, so the term 2x does not have a dy dx, so I'm going to move that to the right side of the equation. So I'm going to end up with 2y times dy dx is equal to negative 2x. I've just subtracted the 2x from both sides. So step 3 says we need to factor the dy dx out of the left side of the equation. This is the only term, so we won't really have to do step 3 in this particular case. We'll watch out for that on another problem. But that brings us to step 4, solve for dy dx. In other words, get dy dx by itself. So we can do that by just dividing both sides of the equation by 2y. Okay, so if I just divide by 2y on both sides, so that way the 2y's will cancel each other out, then we have dy dx by itself. So dy dx is equal to negative 2x. Well, you know what? Look, these 2's are going to cancel each other out. So might as well simplify that right now. And that's just going to give us negative x over y. And this is the final answer. dy dx is the derivative of y with respect to x. So this is the final answer. Remember at the beginning when we were kind of wondering how to find the slope of the curve at this point? Well, this point is the point 2 radical 2 comma 2 radical 2. So we'll call this a quick example 2. Find the slope of the curve defined by x squared plus y squared equals 16 at the point 2 radical 2 comma 2 radical 2. In the previous example, we just found the equation for the slope of the curve at any pair of values x and y. So we can use that to answer this question. So y prime is equal to negative x over y. So that means y prime is going to equal negative 2 radical 2 divided by 2 radical 2. So of course that means that y prime is equal to negative 1. And that is the answer to the question. This is the slope of the curve at this particular point. Example 3. Let's find dy dx given that y to the third power plus y squared minus 5y minus x squared equals negative 4. Obviously, we are about to use implicit differentiation. Can you imagine trying to get y by itself right now? What a nightmare. All right, good thing we have implicit differentiation. Step 1 is to take the derivative of both sides with respect to x. I'm going to spread these terms out a little bit to have room for my ddx's. So I'm going to have y to the third power, and then plus y squared minus 5y, let's see, minus x squared is equal to negative 4. So here come my ddx's. So I'm just going to put a ddx in front of everything. All right, please remember that if we have a situation where the variables do not match, we're going to go ahead and do the derivative, in this case with respect to y. In other words, just do the derivative, use your power rule, and you're going to get, in this case, 3y squared. But because the variables don't match, we then have to go ahead and take the derivative of the y itself separately. Technically, this is the chain rule, and we're taking the derivative now of the inner function, having taken the derivative of the outer function on the previous step. So the bottom line is we will end up with this extra dy dx anytime the variables do not match. So again, here the variables do not match. So I'm going to go ahead and yes, use the power rule and take that derivative, but then I'm going to have this extra dy dx. Okay, let's see. So the derivative of 5y is just 5, but again, the variables do not match, so I'm going to need an extra dy dx. On this next one, the variables do match, so there will not be an extra dy dx. I will just use the power rule and get negative 2x, and that's it. The derivative of a constant is just 0, so nothing else going on there. So that was step 1 of our four-step process. Step 2 is to get all of the terms involving dy dx on the left side of the equation, and we'll move everything else to the right-hand side. In this case, we only have one term that does not have a dy dx. So we just need to move this to the right-hand side. I don't feel like recopying this entire equation just to move the 2x over, so I think you're going to forgive me if I just do a quick one of these. All right, I moved it over, you saw it, you get it. The next step is to factor out the dy dx as a GCF. So I'm going to go ahead and put the dy dx out in the front, and that's going to leave the blue stuff. So I'm going to have 3y squared plus 2y minus 5 is equal to 2x. And the last step is to get the dy dx by itself. So I'm just dividing both sides by all of this. So the final answer is going to be dy dx equals, and we'll just end up with 2x over 3y squared plus 2y minus 5. Please don't forget what this is that we just found. This is an equation for the slope of the curve at any point. So this will give us the slope of this crazy curve that we started off with, whatever this looks like. We're going to have the slope of the curve at any xy point given by this equation. Example 4 is just going to be an extension of example 3. Let's go ahead and take that same equation and find the slope of the curve at a couple of points. Let's start with the point 2, 0. Here's a quick glance at what the curve actually looks like, this crazy looking graph. The point 2, 0 is right here. So if we were just to estimate, it looks like the slope is maybe -1, something like that. Definitely a negative slope, maybe -1. So it's good to just get an estimate going and then see how it turns out when we do it analytically. So if we want to find the slope, we're going to use the y prime equation that we found in example 3. X is 2 and y is 0. So that means we're going to have 2 times 2 over, well, these y's are zeros, so I know they are gone. And then I'm just going to have this -5 right here. So that's going to give us a slope of -4/5. Okay, so our guess was -1. It looked about -1. We can see that this is very close to that, but it's actually -4/5 slope. So let's go ahead and find the slope at the point 0, -3. A quick peek at the graph. 0, -3 is right here at the bottom. Or, it's really close to here. So we're expecting the slope to be something close to 0, right? It looks like it should be a horizontal line. So let's see what happens. Remember, the equation of the slope is the derivative, and x is 0. So that's going to give us y prime is equal to 2 times 0. All right, I guess you can see what's happening here. Over 3y squared plus 2y, so that's going to be 3 times -3 squared plus 2 times -3 minus 5. But look, all the magic is happening in the numerator. In the numerator, we're going to have 0, and in the denominator, we have a non-zero number. It really doesn't matter what that turns out to be. We know it's going to be 0 divided by something, which is just going to be 0. So at the point 0, -3, our guess that it was going to be a horizontal line turned out to be correct. All right, last one. This should be interesting. What's going to be the slope at the point 1, 1? So the reason why this should be interesting is because here's the point 1, 1 right here. And it seems like the tangent would be a vertical line. And we know a vertical line has no slope. So the slope should turn out to be undefined. So let's take a look and see what happens. So using the formula that we found in the previous example, so we have 2x over 3y squared. So that means y prime is going to equal 2 times 1 over 3 times 1 squared. And I'm just going to copy the pattern off of the yellow version here. So this will be, because the y value is also 1. So 2 times 1 minus 5. So what happens here? So I have y prime is equal to 2 in that numerator. 1 squared is just 1. 3 times 1 is 3 plus 2 minus 5. Oh, okay. I'm starting to see what's happening here. So we have this 2. And of course, as you take a closer look, 3 plus 2 is 5. And then we have 5 minus 5, which gives us the 0 that we knew was coming. So this slope is undefined. Just like we thought when we peeked at the graph, the tangent line is a vertical line, slope undefined.